y equals 2x squared minus 3 multiplied by tan half x, where x is between 0 and pi. Part A, find the exact value of x when y equals 0. So if I write down the equation, 0 equals 2x squared minus 3 times tan over half x, then this is telling me that either the 2x squared minus 3 equals 0, or the tan half x would have to equal 0. Now the first equation, I can then say that x squared equals 3 over 2. Square rooting both sides, I find that x is equal to plus or minus root 6 over 2. The square root of 3 over 2 is root 6 over 2. Now x has to be a positive number, has to be between 0 and pi, so I can ignore the negative and just give my answer as positive root 6 over 2. So that's an answer for part A, and notice it says the exact value, so that's the only answer in fact. I don't need to worry about the tan half x equals to 0. That is actually not going to have any solutions in this interval. So I don't need to worry about that. Right, so that's part A done. Let's move to part B. So part B says, given that dy by dx is equal to 0 when x equals alpha. So I need to differentiate and make it equal to 0. Now, in order to differentiate this, I'm going to have to use the product rule, because I've got the product of two functions. I've got the quadratic bit there, and I've got the tan x there, or tan half x there. So let's let u equal 2x squared minus 3, and let's let v equal tan half x. U dash, so differentiating the 2x squared, I get 4x. The 3 will differentiate to be 0. Differentiating the tan half x, well, I know that tan differentiates to be sec squared. So I get sec squared half x. But by the chain rule, I know I'm going to have to multiply by the derivative of the inside, which I'm going to need to multiply by a half. When I differentiate half x, I get a half. So I'm going to have to times this sec squared half x by a half. Now applying the product rule then. So I've got u dash times v. So 4x tan half x plus u times v dash. So that's going to be 2x squared minus 3 times a half sec squared a half x. And this is going to equal 0 when x is alpha. So if I substitute alpha in instead of x, my gradient is going to equal 0. So 4 alpha tan half alpha plus a half 2 alpha squared minus 3 sec squared a half alpha equals 0. Right, I need to make this equation look like this equation. First thing I'm going to do is get rid of this half fraction there, so I'm going to multiply each term through by 2. So if I times that by 2, I get rid of this. If I times this first term by 2, that would become an 8. And obviously timesing the 0 by 2 will still be 0. Next thing I'm going to do is let's think about the these tan half alphas. So tan half alpha, I can think of that as being sine half alpha over cos half alpha. The sec squared half alpha is the same thing as 1 over cos squared half alpha. Now I can see that my next step is going to be to multiply each term by cos squared half alpha to get rid of this. So if I times the first term by cos squared half alpha, and the second term by cos squared half alpha, and the right hand side by cos squared half alpha. So the first term, this is going to cancel with one of those causes. So I would get 8 alpha sine half alpha cos half alpha. The second term, this cos squared here is going to cancel with this cos squared completely and just leave me with the numerator, which is 2 alpha squared minus 3. On the right hand side, the 0 times cos squared half alpha will just be 0. Next, I can see I've got this sine half alpha cos half alpha. Now, let me just remind you very quickly of the sine double angle formula. So I know that sine 2 theta is equal to 2 sine theta cos theta. So if I had, for example, 2 sine half alpha cos half alpha, then I could rewrite that as being sine of 2 times half alpha, or just sine alpha, because the 2 times half alpha would be sine alpha. So bearing that in mind, let me rewrite that 8 as being 4 times 2, because then I've got this 2 sine half alpha cos half alpha, which can be replaced with sine alpha. So that first term will become 4 alpha sine alpha plus the 2 alpha squared minus 3 equals 0. And we can see this is what I needed to show. So I think one of the key things there is we had half alphas here and here, and we wanted to just have a sine alpha. So that was my clue, because I was going to have to do something with the sine double angle formula. Right, that's part B done. We are then told that the iterative formula xn plus 1 equals 3 over 2xn plus 4 sine xn can be used to find an approximation for alpha. Taking x1 is equal to 0.7, find the values of x2 and x3, giving your answers to 4 decimal places. So, to find x2, I'm going to substitute 0.7 in instead of the xn. So I would do 3 divided by 2 times 0.7 plus 4 times sine of 0.7. When I put that into my calculator, I find that x2 is equal to 0.7544, correct to 4 decimal places. To get x3, I am now going to substitute my answer into the iterative formula. So 3 divided by 2 times answer plus 4 sine answer. Obviously the calculator is going to pick up that this is my answer from the previous calculation, to find that x3 is equal to 0.7062. So that's my x3. Moving on to part D now. By choosing a suitable interval, show that alpha is 0.7283 to 4 decimal places. So my suitable interval is going to be the lower and upper bounds of alpha. The lower bound is 0.72825. The upper bound is 0.72835. So we're going to substitute those into our formula. Let's just remind ourselves what formula we are using. It's the formula for alpha, which is this one. This is the formula that has an alpha in it. This is the one that's about the stationary point where the gradient function is equal to 0. So I will do 2 times 0.72825 minus 3 plus 4 times 0.7285 times sine of 0.72825, which is, when I put that into my calculator, minus 0.0005. Most importantly, it's negative. If I now do the same thing with the upper bounds, I get positive 0.00026, so positive. And so we can now write our usual sentence. So sign change in the continuous function so there must be a root in the interval and all numbers in this interval round to 0.7283 to 4 decimal places. And there we go.